So today, ladies and gentlemen, we're going to talk about the periodic table and how it's put together. This is the periodic table, and if you don't have your copy that I gave you in class out, you need to pause the video and pull that copy out. If you've lost your copy, then you're going to want to go ahead and print a copy off the internet of the periodic table, a blank copy or a copy that has just the boxes that aren't colored in, and print that copy off and then come back to taking notes. You can take your notes basically on the back side of the periodic table that you have if you wish. You do not have to type them or put them in your science notebook. They can be on the back side of your periodic table. What is the periodic table? Well, it's an organizational system for the elements. It's basically a way that man has organized the elements, and it's actually ingenious because it's going to tell you a ton of information about each one of the elements. Now, if you've forgotten, an element is basically the smallest piece of matter that you have that cannot be broken down anymore chemically into any other pieces of matter or any other things. So if something cannot be chemically broken down into anything more or anything different, we call it an element. For shorthand, it basically means that you have one type of atom. Now you can have a billion of them, or you can have 10, or you can just have one, but as long as they're all the same type of atom, we call it an element. So who came up with the periodic table? Well, people started discovering elements, and by 1860, about 60 of them had been discovered. And at that point, a chemist, a Russian chemist named Dmitry Mendeleev, decided that we needed a way to organize these elements, and so he suggested we organize them based on their atomic weights, or how much they weigh. Mendeleev, when he put the elements that had been discovered already in order by how much they weigh, he realized that there were actually gaps in the periodic table, places where there should be an element, but nothing was there. And he predicted that later in the future, scientists would discover the elements that were missing and be able to fill them in. And he actually was correct. Scientists have discovered the different elements in between and have been able to fill them in. Now, the genius of the periodic table is that it actually will tell you a ton of information about each individual element based on where that element is located in the periodic table. Periodic table has rows, and those rows are called periods, and they tell you something about the elements. They have columns, and those columns tell you something about the elements. And then they have families, and those families tell you something about the elements. So the way it's organized, if you know how it's organized and you're able to read it, you can tell a lot about the individual elements on the table from the periodic table and from how it's organized. So how is it organized? Well, the first thing is going across, and guys, do not color code your periodic table now. I will tell you when to fill it in with different colors. Okay? But you do need to make a note that going across the rows are called periods. So the rows of the periodic table are called periods. Okay? So this would be the first period, second period, third period, fourth period, fifth period, sixth period, seventh period. Each period basically tells you how many atomic orbitals or how many shells the elements in that row will have. So for instance, let me go back here. This first row is period number 1. It has one orbital or one shell. The second row is period 2. It has 2 orbitals or 2 shells. Row 3, 3 orbitals, 3 shells. Period 4, 4 orbitals, 4 shells. Period 5, 5 orbitals, 5 shells, and on and on. Basically, the rows or the periods tell you how many shells or orbitals there are for that individual element or atom. Then going up and down, you have groups, or the columns in the periodic table are called groups. Now, guys, it's very important to note that this middle portion right here is skipped because these are called transition metals, and they actually have different rules than all the rest. Okay? But this red one here would be group number 1. This orange column would be group number 2. The yellow column is group 3. Green column is group 4. Light blue group 5. Medium blue group 6. Dark blue group 7, and this purplish color is group 8. Again, you skip the middle and skip the bottom. 1, 2, 3, 4, 5, 6, 7, 8. Again, don't color code them, okay? But I do want you to number them. So let's go back to the periods. I want you on your periodic table to write period 1 next to this row, period 2 next to this row, period 3 next to this row, 4, 5, 6, 7. Pause the video now while you do that, and then start me back up again. Okay, now I want you to actually, up here, I want you to write group 1. Here I want you to write group 2. Here I want you to skip these. Here I want you to write group 3, 4, 5, 6, 7, 8. So write the groups in above there. Pause the video till you're done and then start me back up again. Okay, so what do the groups tell you? The groups tell you how many valence electrons are located on the outermost shell. Remember, a valence electron is an electron that is on the outermost shell, the outside shell. And the group tells you how many valence electrons are on there. So for instance, if an element is in group 1, it means it has one valence electron, one electron on the outside shell. If it's in group 2, it has two valence electrons. 3 valence electrons, 4, 5, 6, 7, 8 valence electrons in the outside shell. So the group tells you how many electrons are on the outside shell. And again, we call them valence electrons. So how do I read a square in the periodic table? Well, the top number is called the atomic number. Okay? And that is equal to the number of protons that that atom has. Remember, the number of protons tells you what the atom is. It basically defines the atom. So this is the atomic number. It tells you the number of protons. It also tells you in a balanced or a stable atom what the number of electrons are. So atomic number is the number of protons and the number of electrons. Write that down. That's important. Okay. The letter is the symbol for the atom. Okay. The name of the atom is next. Okay. So this is the name of the atom. And then finally, the bottom number is the atomic mass or the weight of the atom. This is basically equal to the number of protons plus the number of neutrons, and then you round it. Now you might ask, wait, Sullivan, you can't have 0.011 of a neutron. Why is this a decimal? Well, the reason why is because basically they take all the isotopes. Remember, isotopes are the same element, so like carbon, but they have different numbers of neutrons. So you might have a carbon with 7 neutrons, a carbon with 6 neutrons, a carbon with 8 neutrons, a carbon with 10 neutrons. They take all those atoms and they add their weights together and they average them. And so that's why you get the decimal. But basically, you can assume that if you take this number, the atomic mass, and subtract the atomic number up here, that's how many neutrons on average you would have across all the isotopes. Okay, so that's how many neutrons you have. So atomic number, number of protons and electrons. Symbol, short version of it. Name, name of it. Atomic mass, the number of protons, plus the number of neutrons. Okay. Now, based on this information here, you can draw any atom on the periodic table just from looking at its box and where it's located at. I'm going to show you that in more detail in class, but basically if I were to draw this atom, carbon, well, carbon, it turns out, is on the second period. Let me go back. So it is in the second period, so I know it's going to have 2 shells. So I would draw it with 2 shells. And carbon actually is in this green group right here. So that's 1, 2, 3, 4. It's going to have 4 electrons on its last shell, 4 electrons. And then you know how many protons and electrons it has, and you know how many neutrons it has because you can subtract the atomic number from the atomic mass, and that gives you the neutrons. So based on that information alone, you can draw almost any atom on the periodic table. So other than periods, again, rows going across, and groups, again, columns going down. And remember, we skip the middle. So group 1, group 2, group 3, group 4, group 5, 6, 7, 8. Okay. Other than that, the periodic table also has families, and those are color-coded. Here's where you're going to want to start color-coding your table. So start color-coding it now. Okay. The first group over here, the blue group, these are called alkali metals. These are metals that are very reactive, And they don't normally occur in nature all by themselves. Normally they're hooked up with another atom and they make a compound somehow. But these atoms are very, very bendable. Malleable means they're bendable. They're ductile, which means they're breakable. They're great conductors of heat and electricity, and they tend to explode if you put them in water. I love that part. So these are the alkali metals. Alkali earth metals basically is the red group. Again, it's a group of metals. They're metals. They are very reactive, and again, you don't normally find them in nature either, and they often react with air or water as well. Then this whole big yellow group here in the middle, this light yellow group, these are called transition metals. And again, if you're not color coding, you need to be color coding along with me here. Make a little key on the side, put the color, put the notes. Okay? So these are transition metals. They are ductile, which means they're breakable. They're malleable, which means they're bendable. And they conduct electricity and heat. Some of the most common metals that we use are transition metals. Things like iron, nickel, cobalt, gold here, Au is a transition metal. This Fe is iron. Many of the ones, nickel is right here, Ni. So many of the metals that we normally use to make things are transition metals. Then we have down here, this bottom group down here, they're the darker yellow. These are rare earth metals, and many of these are man-made. And that's why many of them will actually have weird names to them. Like you've got Einsteinium, okay? And you've got things like, I don't know, Californium. Okay? They're man-made metals, okay? And again, they're all metals and they're rare and usually man-made. Many of them, not all of them, but many of them are. Then this little light blue group here, these are other metals, okay? So these are also all metals. They are all bendable and breakable. They are usually pretty solid metals and they have a really high density, which means they are packed metals, okay? You'll notice aluminum is one of them. Okay, and lead, Pb is lead. Okay, they're really packed. Okay, metalloids are the purple right here. This purple group, okay? And they have properties of both metals and non-metals, but they're still considered to be metals. Okay, some of the metalloids are used in computers to make semiconductors for computers. So a lot of these are used for making computer chips and things that go into electronics because they're really good at holding an electrical charge. Silicon, if you've ever heard of silicone or silicon, that's one of the ones that they use in computers all the time. Next one, finally we get into the non-metals. So these green ones are non-metals, and notice hydrogen is over here by itself, but it's still green. It's a non-metal. They cannot conduct electricity or heat very well or at all. They're very brittle, and they do not reflect light at all. Okay, so these are the non-metals. Color them green. Now, guys, I know what you're saying at this point. You're freaking out because you're like, there's so many families and there's so much information. Sullivan, make the madness stop. Okay? Don't freak out on this one. We're going to spend a whole week and a half, 2 weeks studying these, and I'm actually in class going to show you different videos that show you each group and show you how each group reacts and what happens with each group. Okay, so we're going to take a day for basically each one of these groups. We're going to take a day for the alkali metals, day for the alkali earth metals. We'll take a day for the transition metals. We'll take a day for the halogens, a day for the noble gases. Some of them we'll skip, but in all, we'll take almost a day for each one of these. And I'll show you some videos of them, and we'll talk about them, and we'll talk about how they react and what they do. So don't freak out right now. I'm just giving you a basic overview of the next 2 weeks. Okay, hang tight. Next group, this pink group. Sorry, this is supposed to be pink. It looks kind of purple too, but it's a different group. It's pink. This pink groups are called the halogens. Okay? These are things that form salts. Okay? So when they come together as compounds with other items in the periodic table, they make salts. Okay? And these exist in all 3 states of matter, solid, liquids, and gases. Okay? So for instance, chlorine right here, Cl, when you put that together with sodium, which is over here, Na, actually it's an alkali metal, but when you put chlorine, the halogen, with Na, sodium, you get table salt. Okay? When you put Br with different things, you get a salt. So these all make salts. different types of salts. And finally, you've got your noble gases. They are noble, okay? They are the brown group, okay? They are all gases, okay? They do not form compounds very easily, so they do not basically hook up with other atoms in the table to make other things very easily. They like to stay by themselves. The reason why is because on their outer shell, they are in group 1, 2, 3, 4, 5, 6, 7, 8. They are in group 8. So their outer shell has 8 electrons, okay, which means that it has so many electrons, their outer shells tend to be full of electrons, and then therefore they don't really want to bond with anything else very well. Okay? They're happy being all by themselves. Now, another thing you need to know before we end the video, let me go back here. I guess we can just use this one. As you go down in the periodic table, things get more dense, okay? And as you go down in the periodic table, reactions become more violent. So for instance, I am going to go back here. The alkali metals. Lithium, when you put it in water, bubbles a little bit. Sodium sparks. Potassium actually catches fire. Rubidium explodes. Cesium explodes big time. And francium, holy moly, if you could get that to explode, it would be like a nuclear bomb going off. So basically, as you go down the periodic table, the reactions become more violent. Same thing here with the alkali earth metals. As you go down, their reactions to the air, a lot of them react with air, some of them with water, but they become more violent as you go down. Okay? The halogens, I think, are the only exception, and we'll talk about that in class. Don't worry about that right now. But the noble gases, as you go down, they become more dense. So for instance, helium and neon are lighter than air. They will float. But argon, krypton, xenon, these all, if you put them in a balloon, will sink. And these down here will sink like a stone. Ka-chewy. Okay? So basically, as you go down, things become more dense. As you go down, things become more violent. Okay?